Hello everybody. Today we are going to study one of the application of Fresnel biprism experiment. Today we will find out the thickness of a thin mica sheet by using Fresnel biprism experiment. So in the last class we have studied Fresnel biprism experiment, and in the same class we have studied one of its application. We found out the wavelength of unknown source by using Fresnel biprism experiment. In this class we'll be finding the thickness of a thin mica sheet by using the Fresnel biprism experiment. So why Fresnel biprism experiment? Why not some other scale like you can use a vernier or a screw gauge, any kind of other scale to find out the thickness, but why you're specially using Fresnel biprism experiment to find out the thickness of a thin mica sheet? It is because you see, here's I have a thin sheet. Okay, this is how it looks like, and the thing is I want to find out its thickness. So if I use a normal scaling like a screw gauge or vernier caliper or any a normal scale, any kind of scale, so because its thickness is so thin, it's so minute thickness, so will not give me the precise value of the thickness of this thin sheets. So that's why we need a more accurate equipment with the help of which I can find out the thickness of this. So now today we will be finding the thickness of this transparent thin mica sheet. Now let's get started. So we'll be using the same experimental setup which we have used for finding the wavelength of unknown source in Fresnel biprism experiment. So same Fresnel biprism experiment we will be using. There will be no any change. We'll be using the same biprism, we'll be using the same single source and the final screen. Everything will be same. But the only thing is that we will be introducing this thin mica sheet whose thickness we want to find out. So here's I'm gonna draw the setup by Fresnel's biprism setup. Here I won't be drawing the biprism in here because it's not needed, but the biprism is there. It is not like you're not using in the experiment. It is there, we are using it, but for the simplification of the figure I won't be drawing the biprism in here. I'll be using just two coherent sources and the final screen. That's it. So here's I have the source, coherent source S1, S2, and here I have the final screen. The center of the screen, I'll be calling it as O. So at the point O, the light rays from S1 source, the light ray from S2 source will hit at the point O and will give you the central bright fringe. Central bright fringe, because the distance traveled by the, if I call it as ray 1 and if I call it as ray 2, the distance traveled by the ray S1 to reach the point O is exactly same as the distance traveled by the ray 2 to reach the point O, and they are taking exactly same amount of time to reach the point O. That's why they'll undergo constructive interference and they'll give you a central bright fringe at point O. Okay, this is what it is. This is the whole picture before introduction of the thin mica sheet in the experimental setup. This is what we will get. Okay, now what I'm doing, so I want to find out the thickness of this thin sheet. What I do is I'll put this thin sheet in the path of any one of the interfering light rays. Either it can be the light rays from S1 or the light rays from S2. Either ways you can get the thickness. So here I'll be putting the thin mica sheet in the path of the light rays from S1 source. So after the introduction, so here's I'm putting the thin sheet having thickness T. So what is the value, what is the expression for this T we'll be finding. Having its thickness T and the mica sheet is having refractive index mu. So after introduction of the mica sheet, the whole interference pattern got changed. The interference pattern won't be same as before. The whole interference pattern got changed. What we have observed is after introduction of the thin sheet, this was before the introduction of the thin sheet. So after the introduction, at the point O, where initially we were getting the central bright, at some other point, I'm calling it as P, at some other point I am getting the central bright fringe, not at the point O. So the position of the central bright fringe got displaced in the upward direction because of the introduction of the thin mica sheet. And you see, what we have noticed is that because of the introduction of the thin sheet, the thickness of the fringes, fringe width won't change. The fringe width did not got changed, but the thing is, all the fringes got displaced in upward with the same displacement. It is not like the fringes which are near to the center got the bigger displacement and the fringes which are away from the center got a less displacement. It is not like that. All the fringes got the same displacement. Here's I'm just showing you the displacement of the central bright. Our point of focus is just central bright, and so that's all fine. Okay. After the introduction of the thin mica sheet, the interference pattern will get displaced. Okay, here in this case, if you're putting the thin mica sheet in the path of light rays of S1, the pattern will get shift upward. If you put the thin mica sheet in the S2, the light rays from S2, the whole pattern will get shift in the downward direction. This is what we have noticed. This is what we have observed in the experiment. So the thing is, after the introduction of the thin sheet, the fringe pattern got displaced. That is all fine. The fringe pattern got displaced. But why the fringe pattern got displaced? That is my question. You see, here's what I'm doing is, I want you people to get the concept. I'm not teaching here just for exam point of view. This is how you have to write this thing in the exam, like this and that. You'll get the marks, that is for sure, not a big deal. But the thing is, you won't get the concept. So my aim is to give you the reason for everything that is happening. Okay, so now we will find out. Now I'll explain you what is the reason behind the shifting of the fringe pattern after the introduction of thin mica sheet. So before the introduction of the thin mica sheet, the light ray from S1 and the light ray from S2 are taking exactly same amount of time to reach the point O. If, for example, if I take the ray 2 is taking 2 seconds to reach the point O, the ray 1 will also take exactly 2 seconds to reach the point O before the introduction of the thin mica sheet. Why? Because the distance is same, that's why they will take the equal amount of time, because they are traveling with same velocity, that is c. If they are having the same distance and they are having the same velocity, so they'll take the same amount of time to reach the point O. Okay, this is what before the introduction of thin mica sheet. The moment you introduce the thin mica sheet, this ray 2 will take 2 seconds, no big deal. Okay, it will take the same amount of time, but the ray 1, there is some problem with ray 1. The ray 1 will not take the 2 seconds to reach the point O. It will take a bit a bit more time than the 2 seconds. Why? Because the ray 1 is traveling through a material, a thin transparent material. This transparent material is having some refractive index mu. We know that when the light travels in some kind of medium, the velocity of the light will decrease. Okay, so here's normally it was taking 2 seconds. Because of the introduction of the thin mica sheet, the light ray has to travel through it. So in this path of traveling, it won't be traveling with c velocity, it will be less than the c. Okay, it will be less than velocity of light. Because it is traveling with less velocity, it will be taking more time to reach the point O. That's how it won't reach with with this time. It will be taking a bit more time. For example, if because of the introduction of the thin mica sheet, the light ray got delay of 0.5 second, so it will be having 2.5 seconds to, it will take, the ray 1 will take 2.5 seconds to reach the point O. Because of this delay, there will be, so that's why you will be getting not bright but any other thing, you will be getting dark thing, you will be getting dark fringe over there. Because, so that is the reason why we are not getting the central bright at point O. Instead of that point, we are getting the central bright at point P. Now we'll see why, what is the reason we are getting the central bright at point P. This is the central bright. After the introduction of the thin mica sheet, here's where we are getting the central bright. Instead of the central bright was here, the central bright got displaced in the upward direction. Okay, so now we'll see to have a central bright, the condition is that the path difference between the two rays should be 0, then only we will get the central bright. Initially the central bright was here, this is the point where the path difference between the ray 1 and the ray 2 got 0, but now this is the point where the path difference is 0. But you see the physical path difference, we have travel this way. If we look at the physical path difference, there is some physical path difference between the, if I call it as ray 1 and this as ray 2. There is some physical path difference between ray 1 and ray 2. Why? Because the ray 2 is traveling a bit longer distance as compared to the ray 1. The ray 1 is traveling the shorter distance as compared to the ray. So there will be some physical path difference between S1 and S2. And we know that this is D, and the distance from the final screen to the sources is L. So the physical path difference between S1 and S2, the physical path difference is dxn by L. This is the physical path difference between S1 and S2. But because of the introduction of the thin mica sheet, there will be a path difference. That is, the optical path difference. So because you have introduced the thin mica sheet, there will be an optical path difference, that is T into mu minus 1. This is the optical path difference got introduced due to the thin mica sheet. If this path difference got exactly equal to this path difference, the total path difference will be at point P will be 0. If the total path difference got 0, we will get the central bright over there. In other words, because of the thin mica sheet, as I told you earlier, the velocity of light will decrease. So because the light is traveling through this mica sheet, well, when the light ray is traveling through it, its velocity will be bit lesser as compared to the velocity of light in air. So because of that less velocity, the light ray, instead of reaching with the time 1.5 second, it would take 2 seconds. Where is that 0.5 second that lagging of time came because of the introduction of the thin mica sheet? Now there is no any time difference between the ray 1 and ray 2. If there is no time difference, they will be meeting with the same physical positions at the point P. So that's how you will be getting the central bright at point P. This is the reason. So now we will find out the path that light ray has traveled to reach from S1 to P. Okay, so the path that light ray has traveled in air to reach from S1 to P is S1P minus T. This is in air with c velocity, and there's one more a smaller path that light ray is traveling, that is in the transparent medium, the transparent mica sheet, that is this much path. This is the thickness, means this is the path that light ray is traveling. So this length, this path is in mica sheet with, I'm calling the velocity that light ray is traveling the velocity of light in the mica sheet, I'm calling it as c sub g. Now the total time that light ray has taken to travel from S1 to P, to cover this distance from S1 to P, is the total time from S1 to P is this distance S1P minus T. With what velocity this distance has covered? With c velocity. So displacement, how much distance it got traveled, with what velocity that distance got traveled, that would give you the time. Okay, and this thing plus this much path with this velocity, and we know that c by cg will give you, with the help of this expression, the total time will be S1P minus T plus T divided by C into mu. This would give me S1P minus T mu minus 1 divided by C. So this is the total time that light ray has taken to cover the distance from S1 to P. So with this expression, I can get the path that light ray has taken to reach from S1 to P is, the path S1 to P will be S1P minus T mu minus 1. This is the path. Now I want to find out the path difference difference at point P. The path difference at point P is the path S1 to P in air, not S1, S2 to P in air, S2 to P in air minus the path S1 to P, path S1P. So we got the expression for S1P, substitute that in here, and we know from the Fresnel biprism experiment, okay, if I substitute that in here, I would get x d by L minus t mu minus 1. This is the path difference. Okay, now for the nth maxima, the path difference, so the path difference for the nth maxima would be the nth maxima path difference will be x lambda. If I call this equation as 1 and this equation as 2, so 1 and 2 I can write, because I have generalized this equation for the nth maximum, so here instead of x, here x sub n will come. So the position of the nth maxima, so the position of the nth bright fringe will be x sub n is equals to equation 3. So if I make the thickness of this thin sheet to be 0, what would I get? The position of the nth maximum will be now x sub n is equals to n ln lambda by d. This is the position. So this equation is somewhat similar. This is the same equation that we have got in the Fresnel biprism experiment for the nth bright fringe. So if the thickness is 0, means there is no mica sheet. If there is no mica sheet, you would get the same results as that of the Fresnel biprism experiment. So this is the position of the, I'll call it as the, so this is what it is, like you see the position of any nth bright fringe, it was here. The moment you introduce the mica sheet of thickness T, the position of the nth maxima got displacement. I am calling the displacement S. If I want to find out the expression for the displacement of the fringes, what I have to do, I have to subtract this position with this, then I will get the displacement of the fringes, and that is what I am going to do now. So the displacement of the fringes due to the introduction of the thin mica sheet is, so you see in the expression of the displacement there is no any dependence on n. So n stands for the order of the fringes. So for first fringe, either it is for first fringe or it is for the fourth fringe or any fringe, the shift, the displacement would be same. That's why there is no any dependence on n here. The equation is free from n. So with this expression we can find out, our aim was to find out the thickness of the thin mica sheet. Yes, I have T. So T is equals to the thickness of the thin mica sheet is D, the displacement, S divided by mu minus one, there will be L also, this is the expression which will give you the thickness of thin mica sheet. This is how we find out the thickness of thin transparent material by using the Fresnel biprism experiment. So that's it for today. Thank you so much.